All right, so today's video is all about using the ideal gas equation to solve for some different variables. So what we call that is we're going to be calling that applying the ideal gas equation. So from yesterday's video, we learned that the ideal gas equation is equal to the pressure of the gas times the volume is equal to the number of moles times that gas constant that never changed, that 0.0821 liters atmospheres over Kelvin mole times the temperature, obviously in Kelvin. So now what we're going to do is we're going to take this equation that we learned yesterday and we're going to manipulate it and move it around a little bit, and we're going to be able to solve for some different things. So as we know, the pressure, the volume, the moles, and the temperature, those are things that we've already been able to solve for, and we need to be able to write the equation so that we can find any of those four variables. Okay, what we also know, looking at one of the examples from yesterday, is that when you find the moles, you can use those moles and the molar mass from the periodic table to find the mass of whatever gas you're referring to. So when we take those two together, when we take the moles and we take the mass, remember that you can take the moles and you can say 1 mole on the bottom and the molar mass on the top, and then moles will cancel, and that's how you get the grams, or the mass, of that gas. And we've also learned, going back to the very beginning of the year, that the density of anything, whether it be a gas or not, is equal to the mass of it over the volume. So we're going to use all of these things. We're going to use mass, we're going to use some density, we're actually going to be using molar mass as well with our ideal gas equation. So with this formula, we're going to manipulate the ideal gas equation, and we're going to be able to solve for density. And let me show you how we're going to do that. We know, like I just showed you, that N is equal to moles. A new letter that we're going to use now is capital N, and capital M, and that capital M stands for the molar mass. So what we did when we had the moles is we took the moles and then we said 1 mole times the molar mass times the grams equals the mass of the gas. So what we can say there is that N moles is equal to the mass divided by the molar mass. Notice the different m's there. That little m is just the mass of that gas. So if you have grams, say we have grams, and we say we have 25 grams of helium. To convert that to moles, you put your 4 grams on the bottom and your 1 mole on the top. So then your grams will cancel. So we're taking the mass, little m, and we're dividing by big M, which is the molar mass, and that gives us the moles of the gas, which is our letter N. So we know, having said that, that N moles equals mass over molar mass. So what we can do is we can use PV equals nRT, and we can substitute that into our equation where our moles are. So when we do that, the equation becomes PV equals little m RT over big M. So again, this is just the mass of the gas, and this is the molar mass of the gas on the bottom. Okay, now we're going to do a little bit of algebra here. We're going to move this molar mass on the bottom here. We're going to multiply both sides by that number, and so we're going to end up with MPV equals MRT. Okay, and now what we're going to do is we're going to take our mass here on our right side. And remember, we're trying to find density, and density, as we know, density equals mass over volume. So what we're going to do is we're going to divide both sides by volume. And then what we're also going to do is we're going to divide both sides by R and T. And let's look at what that does. The R on this side and the T on this side cancel. The volume on this side cancels. And so what we have left is we have mass over volume on this side equals the pressure times the molar mass on the top over R times T. So overall, our equation is the density of a gas, which is just that mass over volume, equals the pressure of the gas times the molar mass over R over T. So this is a big equation. That's an important one. The density equals PM over RT. One of the easy ways that I remember this equation is that I remember that PM is kind of like the afternoon or the nighttime. And so one of the ways that I remember it is I think of nighttime over, and RT stands for, I don't know, something like right time. So nighttime over right time is how I remember the density equation. Now, if we move this equation around a little bit more, so D equals PM over RT. If we move this equation around a little bit more, another thing that we can find that we haven't been able to before is the molar mass of the gas. One of the ways that we've learned how to find the molar mass is by using the grams and using the moles. If you divide the grams by the moles, you get molar mass. In this case, though, if we multiply both sides by RT and then divide by P, we're going to get the molar mass is going to equal the density times R times T by moving those up there. And then by dividing by P, we get this equation. The molar mass of a gas is equal to the density of the gas times R times the temperature divided by the pressure. And so these two equations together, these are two important equations in terms of understanding the gas laws. Remember, the way I remember the density equation is nighttime over right time. So nighttime, PM over RT, right time. And the way I remember the molar mass equation is DRT altogether. It's kind of like dirty. And then you've got P on the bottom. So I remember molar mass as dirty P. So we've got the dirty P equation and the nighttime over the right time equation for both of those. Okay, so here's an example of this. It says, what is the density of carbon tetrachloride vapor at 714 torr and 125 degrees Celsius? So first of all, whenever it asks you for the density, the first thing you want to think is, okay, can I solve this problem just by doing mass over volume? I don't see a mass and I don't see a volume, so that equation is not going to work. But it's a good idea to use the easiest equation available to you when you're doing one of these problems. So since that doesn't work, now we're going to have to use the nighttime over the right time equation. Okay, so our pressure is 714 torr. We need to get that into atmospheres like always. So we're going to divide by 760. The molar mass of carbon tetrachloride, so this comes back to before second semester, you being able to know write the formula for that compound. So carbon tetrachloride, tetra stands for 4, so that's CCl4. And so using that formula, now we can go to the periodic table and get the molar mass, because remember, that's what we need. That's what that big M stands for, is for molar mass. So we have 35.5 times 4 of them, because there's 4 chlorines. And then what that is, we're going to add 12. That's carbon. And I get a mass of 154 grams per mole. And that's all going to be over R 0.0821 liters atmospheres over Kelvin mole. And then the temperature is 125 Celsius plus 273 equals 398 Kelvin. Now in this case, up here, remember this changed to atmospheres. So if we've done this again correctly, if we got the density, it should be grams on the top and liters on the bottom. So let's see if that actually happens before we actually look at our numbers. Atmospheres over atmospheres, moles, moles, Kelvin, Kelvin, everything is canceling. except on top we have grams, and on the bottom right here we have our liters. So I know that I have it set up correctly. 714 divided by 760 times 154 divided by 0.0821 divided by 398 gives me a density equal to, again, I'm just looking at my numbers here, 3 significant digits, 4.43. And again, use your units, grams on top, liters on the bottom. And that's my final answer, 4.43 grams per liter. Okay, here's another example. It says a series of measurements are made in order to determine the molar mass of an unknown gas. So right away I'm thinking, okay, molar mass. If I have the mass and I have the moles, I can just divide them. Or I can use the dirty P equation, however I want to do it. Those are my two different ways I can find molar mass. So it says a large flask is evacuated and found to weigh 134.567 grams. It's then filled with the gas to a pressure of 735 torr and 31 degrees Celsius and reweighed. Its mass now is 137.456 grams. So we notice when it was empty, when it was evacuated, it weighed this, and now it weighs this. So right away what I'm going to do is I'm just going to figure out the difference between those two, because I know that's going to tell me the mass of my gas. 137.456 minus 134.567 equals, so I know my mass is going to equal 2.889 grams. And then it says the flask is filled with water at 31 degrees Celsius and found to weigh 1,067.9 grams. The density of water at this temperature is 0.997. Calculate the molar mass of this unknown gas. Now, this is a challenging question because there's a lot of numbers. So instead of trying to go, okay, how do I solve this problem? What I want to do is I want to just do what I know I know how to do. So I already did something here. I got the mass of my gas. So I know that to get the molar mass, if I've got the grams, really all I need is the moles of the gas. That would work. Or I could also use this information here. So let's see. If we know that the final, that the container weighs 1,067.9 grams with water, and the initial mass was 134.567. I'm not sure if this is going to help, but I'm going to subtract those two numbers. 1,067.9 minus 134.567. And that gives me a mass of water equal to 933.333 grams. Okay, then they also tell me the density of the water. And that's interesting to know, because if we know the density of the water, remember we're talking about a gas here, not this liquid water stuff. But if we know the density of the water and we know the mass of the water, I assume that we can find, since density equals mass over volume, we should be able to find the volume. So if we come over here, we know that volume is equal to mass over density. So our mass, again, was 933.333 something something. How many threes were there? 3 threes. Grams. Our density, as they tell us here in the problem, is 0.997. 0.997 grams per milliliter. And again, remember, I'm just doing this because I'm trying to, I don't know necessarily what I'm doing here. I'm just trying to do something that is going to get me closer to maybe me going, oh, okay, now I know what I'm doing. So I'm going to divide those two, so that means the volume is equal to 936 milliliters. Now, does that help me at all? Because it's in the same container as the gas was. The flask was empty. They put some gas in it. Then they let the gas out. They put some water in there. What that does tell us, if it was in the same flask as before, so if we had this flask and we filled it up with some gas, reweighed it, and then we took the gas out and then we took some water and put the water in there, it's the same flask. So if we know the volume of the water, can't we say that the volume of water is also going to equal the volume of the gas, since they were both in the same flask? And really, that's the key to understanding this problem, is knowing that those two volumes have to equal each other. Because if we know that, now we can come back to our original equation here. Molar mass equals dRT over P. Molar mass equals density. The density is the mass over the volume. And so our mass, again, was 2.889 grams of the gas. 2.889 grams divided by the volume, which we need in liters. We're just going to move the decimal point 3 spaces over. So that is the density of our gas, times R, 0.0821. And I'm running out of room here as always, so let me get rid of some of this. And let's see, what's our next? So DRT, our temperature. The temperature, it tells us, is 31 degrees Celsius. 31 plus 273 is 304 Kelvin. And oops, I forgot my units here on this one. Liters, atmospheres, Kelvin, mole. And then on the bottom is our pressure. The pressure they give us is in torr. We got to put that into atmospheres, so we're going to go 735 divided by 760, and that'll be atmospheres. Okay, now again, molar mass is grams over moles. That's how you determine molar mass, is the grams over the moles. So let's see, liters over liters, Kelvin and Kelvin, atmospheres and atmospheres, and it looks like I have grams left on the top and I have moles left on the bottom. So that tells me I did it okay. So now I'm going to take 2.889, divide it by 0.936, times by 0.0821, times 304, divided by, and then in parentheses, 735 divided by 760, close parentheses. I'm not sure if those parentheses are necessary or not. But I get a molar mass equal to 79.7 grams per mole. Now, I'll be honest with you, that's a pretty challenging problem. Typically, they aren't that difficult. Normally, it's just here's the numbers, put them into the equation. But I wanted to give you one that you are more likely to find on a test or something like that. That's about as challenging of a problem as I would ever give you dealing with molar mass or density, something like that. But again, remember the key here is understanding that when they ask for density, try to do it the easy way first. If you can't, then do it that way. If they give you the mass and they give you the volume, that's the easiest way, and do it that way. That's the correct way to find the density. Okay, same thing here. If they give you the mass and they give you the moles, just divide them and get your molar mass. If you have to, use this equation, but not unless you need to. Okay, now one of the things that the ideal gas equation can be used for as well is to solve for different variables. So for example here, the safety airbags in automobiles are inflated by nitrogen gas generated by the rapid decomposition of what's called sodium azide, NaN3. So this NaN3 here breaks down, it gets heated up really quickly inside your steering column, and when it does that, it creates a large amount of nitrogen gas, and that's what blows up your airbag. So it says if an airbag has a volume of 36 liters and is to be filled with nitrogen gas at a pressure of 1.15 atmospheres, at a temperature of 26, how many grams of NaN3 must be decomposed? So basically, they're giving us information about this gas, but then they're asking us about something else. And so what this question is doing is it's combining what we know about gases, but also what we know about stoichiometry. So what we're going to have to do is, the first thing we're going to have to do is we're going to have to figure out our moles of nitrogen. To do stoichiometry, you have to have moles. So we're going to go N equals PV over RT. The pressure 1.15 atmosphere. The volume 36 liters. R 0.0821. And the temperature, 273 plus 26, is 299 Kelvin. So let's get that first. So 1.15 times 36 divided by 0.0821 divided by 299 equals 1.69 moles of N2. So now the question is, if you're going to produce 1.69 moles of N2, how much NaN3 did you need to start with to make that? So now we're going to switch gears and we're going to go from gases back to stoichiometry. And from my balanced equation, 3 moles of nitrogen, because it's nitrogen over here, are produced from 2 moles of NaN3, because of that 2 right there. And now my last step, 1 mole, and I'm out of room, of NaN3 has a mass of 23 plus 42 is 65 grams. And again, that's of NaN3. So now I can take my answer, times by 2, divide by 3, and then multiply by 65. And I get a final answer of 73.1. I guess only 2 significant figures here. So 73 grams of NaN3. So this is a question that's involving not only the gas laws, but also some stoichiometry as well. Okay, so we determined the moles of nitrogen first using the gas laws, using the ideal gas equation. Once we determine that, then we use stoichiometry to find the mass of NaN3. Okay, here's one more example here, and then that's our last one. So they want to know, this is ammonium sulfate, a big fertilizer. This is the reaction that makes ammonium sulfate. They want to know how much, or the volume of NH3 needed to react with all of that sulfuric acid. So think about this from a chemical company's point of view. They don't want to waste anything, so they're going to use as least as much of the reactant as possible. So to convert from sulfuric acid, they want to know how much ammonia do you need. So again, it looks like we're starting with 87 kilograms of sulfuric acid. So the first thing we want to do is convert those to grams. 87,000 grams of H2SO4. And now we need to convert. We need to convert from those to moles of NH3. So sulfuric acid has a molar mass of 98.1 grams in 1 mole. And then from my balanced equation, 1 mole of H2SO4 from here reacts with 2 moles of NH3. Now at this point, we could get grams of NH3. We could use the molar mass and we could get grams. But remember, we're trying to find the volume. And we know that volume of a gas is equal to nRT over P. And that N is moles. So really, we can stop right here. And we can say 87,000 divided by 98.1 times 2 is equal to 1,773. Looks like we've only got 2 significant figures here, so we're going to have to round that to 1,800 moles times 0.0821 times the temperature. 273 plus 42 is 315 Kelvin, and the pressure is 15.6 atmospheres. So I'm going to take 1,800 times 0.0821 times 315 divided by 15.6. and I get a volume of, again, two significant figures, 3.0 times 10 to the third liters. Basically, that's 3,000 liters in scientific notation with only two significant figures. Okay, so as you can see, now what we're going to be doing is we're going to be combining stoichiometry with the gas laws and being able to do this step down here that also will include using gas laws as well.